Today we're going to take a look at section 11.4, geometry in 3 dimensions. Not everything, but most of what we've done so far has been geometry in 2 dimensions. So we're going to do 3-dimensional geometry today. Some vocabulary to start with. A simple closed surface has one interior, which is hollow or empty, and one exterior, and no holes. Okay, so a donut, the kind with a hole in the middle, would not be a simple closed curve. Simple closed surface, excuse me, okay? Because it's got a hole in the middle of it. A solid is the set of all points on the surface plus, and then as well as, all of the interior points. So if you thought about like a basketball, that would be a simple closed surface, but you thought about like a medicine ball, which is actually filled with something, right? It's got something solid inside of it, or a weighted ball like you see over at the gym, that would be a solid. Simple closed surfaces. A sphere is one of those. It's the set of all the points in space that are a certain distance from a single point. That single point is called the center. The distance from the center to the sphere itself is called the radius of the sphere. Another type of simple closed surface is a polyhedron. The plural of polyhedron would be polyhedra. I'm not going to promise you that I'm going to remember to use the right one in the right context, because that one, it's like syllabus and syllabi. They just kind of come off my tongue, interchangeably. They're really not, but they're close. They have sides. It's a simple closed surface with sides that are shaped like polygons. So remember our polygons, we went through a whole bunch of them last time. Hexagons and triangles and nonagons, all those. Those are polygons. So all the sides of a polyhedron are polygons. We call the sides faces of the polyhedron. The vertices, which is the plural of vertex, of the polygonal faces are called the vertices of the polyhedron. The sides of the polygonal faces are called the edges of the polyhedron. So if you kind of think about it, the vertices are the corners. The sides or the edges would be the line segments, and the faces are the planar objects, the flat pieces. Does anybody play soccer? Soccer ball is a really good example. Soccer ball is not really exactly round, right? If you actually took it apart and laid it flat, you would have all these pieces that are actually polygons. They're these flat surfaces. Now, there's so many of them that it has a very roundish shape, right? But if you take all the pieces apart, the way it's created is more like what they're describing for a polyhedron. So we're going to go through and identify just yeses or nos, which ones were polyhedron. Okay, so is the first one a polyhedron? Yes, it's got these flat faces. They're triangles and they're rectangles, right? Triangle on top, triangle on bottom, rectangles around the object. This next one, we'll have names for these in a little bit. This next one, is it a polyhedron? Yes, it is. We have a square or a rectangle shape on bottom, and then there's triangles that are sort of around it. The third one, that's a sphere. Is it a polyhedron? No, it's not a polyhedron because it doesn't have those polygon faces, right? It's circular all the way, so to speak. How about the next one? Also a no. I've got circles on the top and bottom. Circles are not polygons. How about the next one? No. Do you know what's wrong with the next one? There's a couple of things. Has a hole is the biggest thing, right? Even if the hole weren't a cylinder, a circular kind of shape, it would still be a problem just because it's a hole. So it's kind of got a double problem. Not only does it have a hole, but it also has a circular kind of hole. How about the last one? Yeah, that's also a no. What's wrong with this one? Yeah, it actually has 2 insides, right? Or it crosses, the edges cross over themselves, those kinds of things. So it's not got a simple closed shape. All right, so now we're going to talk about some specific types of polyhedron. The first one is called a prism. A prism is a polyhedron with two congruent parallel faces called bases. So in my picture, it's the blue triangle on the top, blue triangle on the bottom. The other faces that are around the object are called lateral faces, and they're always shaped like parallelograms. If it's a straight up and down or a right prism, then those faces around the edges, the lateral faces, will be rectangles. If it's leaning or tilted, then, which is what we call oblique, then literally they won't be rectangles, but they still will be parallelograms. They'll have a shift or a tilt to them. We name prisms by the shape of their bases. So this prism right here has the blue. What are those blue shapes? They're triangles. So this is a triangular, because they're triangles. It's straight up and down, and the reason I know that is because they mark the 90-degree angle right here. So that means it's a right, because it's straight up and down, and it's a prism. So this is a triangular right prism. So we're going to name a few more now. I have 4 more for us to name. And I'll draw in the right angles that are not drawn in because, like I've told you before, it's really hard to get resources from online that do exactly what you want them to do. Those are the 2 angles that are right, the first diagram and the third one. So on the first one, what is the shape of the base, visually speaking? Yeah, it's supposed to be a square, so I'll mark it that way. It's a square, and I'll put the right angle in there too. Okay, so this would be a square, right, yeah, because it's straight up and down, prism. How about the second one? Start with the base. It's a pentagon, so we say pentagonal. Is it right or is it oblique? It's oblique because it's leaning, and then it's a prism. How about the third one? Yeah, octagonal, but we would say octagonal. If you ask somebody else, they might say octagonal. I say octagonal. Right or oblique? Right. And it's a prism. How about the last one? It's triangular. Oblique, because it is leaning. Prism. Okay, so that's our first type of polyhedron. Second type of polyhedron is a pyramid. A pyramid is a polyhedron determined by a polygonal face called the base, and a point called the apex, not in the same plane as the face. So you know, most of the time when we think about it, we think Great Pyramids of Egypt kind of shape, right? So the apex is sort of like up in the air and the base is on the ground. That's our image in our head. Of course, if we flip it upside down, it doesn't make it any less the same object. That's just not our visual imagery. The pyramid's shape comes from the triangular faces. Okay, so all of the lateral faces are triangles, and they're determined by the point at the top, the apex, and each edge along the polygon at the bottom. The altitude of the pyramid is a perpendicular segment to the apex from the base. From the apex to the base. It's the height. If you were to take, this picture kind of makes it look hard to see, but if you were to take this shape and go straight down to the triangle forming a 90-degree angle, that would be the altitude or the height of your pyramid. Now, the pyramid still may slant, but you still have to go straight down. So it may not go to the center of the pyramid. If the pyramid's slanting, it's not going to go to the center, okay? But it would still be the height. And then the pyramids are named for their bases, just like the prisms were. So we look at the base. In this case, there's a triangle down there. So if we were to label this one, we would call it a triangular, because it's a triangle on bottom. Right, because it is straight up and down, pyramid. Triangular right pyramid. All right, I think I have a couple more things on here. Oh, I mentioned it, I already identified mine, but we'll film it now. If the base is a regular polygon and the altitude intersects the base's center, which it did on my last picture, then we would have a right regular pyramid. So regular identifies the shape at the bottom. Right identifies that it's hitting down at the bottom at that 90-degree angle at the center. Right, so this point would be the center of the object. If this particular one is a regular pyramid, it would mean that I've got, a regular shape. It would have to be a square at the bottom. So this would be a square right regular pyramid. If the altitude does not intersect the base's center, right, if the shape is leaning, we still call it oblique. It's an oblique pyramid. It can be very difficult to draw these. I'm not an artist, and so I find them difficult to draw myself. So some keys to helping you draw them in a way that sort of visually makes them look correct. Draw the base first. Is it a square? Is it a rectangle? Is it a triangle? Start with the base. Draw parallel vertical segments of equal length. So if you've got a triangle as the base and you're trying to do a pyramid or a prism, we'll do a prism first, you're going to go straight up and down, right, for a prism, the same length. So for instance, if I were drawing a base that was a triangle, like here's my triangle, all right, there's my triangle, and I want to make it a prism, then as I'm drawing my segments up, if this one went up this far, the second one has to go up the same distance. So do you see how those look like they're the same length? And again, you're doing it as best you can because none of us are perfect at drawing, though some of you are probably better than I am. So you start with drawing those 3 vertical pieces next, and then you connect to the end points of the segments. So this would be my approximate 3D shape. So they're not perfect because the triangle at the bottom is not exactly like the one at the bottom, right? The top and the bottom, I mean. But they're pretty close. This is certainly not the worst picture I've ever drawn. Okay? But it helps to have those features in mind as you're drawing them. All right, another type or description for a polygon, convex. A convex polyhedron, man, I can't speak, I'm so sorry. A convex polyhedron is a polyhedron where any segment connecting 2 points in the interior of the polyhedron is itself in the polyhedron. This is the analog to what it looks like for a convex polygon, right? If I can draw a line segment between 2 points and it goes outside of my shape, then it's not convex. So if you're taking a look at these diagrams right here, which of the following would be convex? The first one, the second, or the third one? The first one is what? Concave. The first one would be concave or not convex. This one is not convex. And the reason is because I've got this indent here, right? Because I've got this indent, there are places on this side, whoops, I'm going to use a different piece, on this side that if I connected him over here, I would go outside of the shape. I would cross outside. So that makes it not convex. How about the second picture? It's convex. And the third one? Yeah, it's convex. Now, we mentioned the word regular when we talked about the bases of like the pyramid or the prism. If you have an actual regular polyhedron, then it means all of the faces, lateral, bases, whatever faces you have, okay, the flat pieces are all identical. They're congruent to one another. So a convex polyhedron whose faces are all congruent, regular polygons. Each vertex of a regular polyhedron has the same number of edges. And there are only 5 of these guys. I mean, that's it. The 5 you see in this picture are the 5 regular polyhedron. There aren't any others. Now, they all have names. So if you flip to your next page, you're going to see the fun names. I heard a little bit of a groan there. I know you've seen and heard the second one. We use that one a lot. right? The other ones you may not have heard very much. Sometimes people have heard of the first one, a tetrahedron. You've certainly seen them, whether you've heard them referred to like this or not. So I like this chart. It's a wonderful chart because it's got all the pictures on the right and it's got all the details of the pieces in between. So we'll run through them quickly because I know you can reference them later. If you really like this piece, this table, you'll be able to put this on your note card or pieces of it on your note card and that kind of thing. A tetrahedron has 4 faces. You can see them in the picture. The faces are equilateral triangles. And the vertices have 3 lines that hit at each one of them. A cube has 6 faces. They're all squares. Again, each vertice has 3 edges that end at each vertice. An octahedron is not an octagon. Okay, that's a common misconception. Octahedron does have 8 faces though, but the faces are all equilateral triangles. And at each vertex there are 4 edges. A dodecahedron has 12 faces. Those 12 faces are all regular pentagons. And there are 3 edges that intersect at each vertice. And the icosahedron has 20 faces. They are equilateral triangles as well. You notice lots of equilateral triangles here, right? And each vertex has 5 edges that hit at it. Now, regular polyhedrons, whatever, they have what are called nets. Okay, so what is a net? So if you were to take one of these objects, the 3D picture, and you were to cut it along the side so that you laid it flat, kind of like my description of my soccer ball a minute ago, right? If the seam ripped and you laid it flat, what would it look like? Well, that image, that 2-dimensional image, is called a net. So these are the nets of the 5 regular polyhedron. So if you were to fold along the dotted lines and fold along the solid lines, like on my cube right here, if you folded along here and here and here and here and you wrapped it up on top of itself, you would have a cube. And the same would be true for each of these pieces. You can imagine folding along the dotted lines of the tetrahedron here, and it folds up into that triangle pyramid shape, right? The octahedron, the dodecahedron, and the icosahedron. So if we had time, what I would love to do with you is I would love to actually print these out, right? And fold the paper up and use tape and actually create them. That would be wonderful. And that would be the kind of activity that you could do with children. Agreed? So I will tell you, my son came home the other day with something that I did not know was taught in 3rd grade. And when we get there later in this semester, I'm going to make mention of it because I hadn't known that before. I would have thought that it was much later on that we talked about something. So I try to help you guys out to understand, but 3rd grade, they're doing some of the things that we do later in this book that I didn't know that. So this kind of an activity is math, but it's very hands-on math, right? You can actually count the edges and the vertices and all that kind of stuff, and you can fold them up. Now, there's a guy, a mathematician named Euler. This is not Euler. That's what it looks like. Okay, it is Euler. So write yourself a little note. That's how it's pronounced, Euler. Euler's formula says that for any polyhedron, not just the 5 that we talked about, but any polyhedron, that if you take the vertices plus the faces and subtract the edges, the number of vertices plus the number of faces minus the number of edges, it will always equal 2. And we're going to check it for just a couple of our images that we can see well. We'll do it for the first 2. I know it says we're going to do it for 3, but we're just going to do it for a couple of them. It says check Euler's formula holds for 3 of our 5 regular polyhedron. We're just going to do it for the tetrahedron and the cube. So let's do it for the tetrahedron, because the image is pretty easy to count from. If I were counting on the tetrahedron, how many vertices does the tetrahedron have? It's 4. So over here in your tetrahedron, you've got 1, 2, 3, 4 vertices. All right, faces. How many faces does it have? It's also 4. There's 3 around it, and then there's 1 on the bottom. I will say my son's done that, and he's in 3rd grade, where they're counting faces, and that's really hard for him to see when they're hiding images that are hidden behind stuff. That's a tricky thing. So that 3D visualization is not intuitive for children, something you can help them work with for sure. So faces are 4. And then we have our edges. How many edges do you see in this object? 1, 2, 3, 4, 5, 6. You're right, there are 6. So if we have our 6 edges. And we're going to verify that this holds. If I take vertices plus faces minus edges, do I get 2? Well, this is 4. Plus 4 minus 6, is that 2? Yes, it is. So let's do the same thing for cube. I'm going to let you do the counting. Back on your diagram. We have, what is first? Vertices. How many vertices does our cube have? It's 8. There's a square on the top, a square on the bottom. How many edges does our cube, I'm sorry, faces is next, my bad. How many faces does our cube have? 6. 4 lateral faces, base on top, base on bottom. How many edges? 12. 4 around the top, 4 around the side, the lateral ones, and 4 on the bottom. So vertices plus faces minus edges, does it equal 2? Yeah, so we have 8 plus 6 minus 12, and it does in fact equal 2. And we could continue this for the other 3 shapes, but I think you get the idea. Is that good? And it's not specialized to these shapes. We could do it for any of the prisms, any of the pyramids that we have, and it will still work, okay? It will still work. Okay, a couple of non-polyhedron to talk about that we see and encounter on a regular basis. Cylinders and cones. So a cylinder is a simple closed surface that is not a polyhedron. A cylinder has bases that are not polygons and a lateral surface with no edges. It's smooth. What objects in your real life are cylinders? Give me an example. Water bottle. Nothing else, huh? There's one you use multiple times a day. Toilet paper. Oh yeah, that one. Paper towels, right? Yeah, I know they've got the holes in the middle of them, so we're ignoring that fact for the moment. Cans, you know, whether it's cans of soda, cans of green beans, cans. We have cylinders all over the place. Use cylinders a lot. Now, most of the cylinders, in fact, maybe all the cylinders we just mentioned, are in fact circular shape on top and circular shape on bottom. That's not a requirement for it to be a cylinder, okay? And that's exactly why I chose the first image on the top here to show you that that's called a cylinder too. And that shape is certainly not a circle on top, right? It's an odd-looking shape. The cylinder you know and love is called a right circular cylinder. Almost all the objects we just mentioned, pretty much all of them were, right? We have a circle on the top, circle on the bottom. If it's not straight up and down, we don't call it right, we call it oblique. If it were not a circle like this shape over here, this one is still right? It's still got this right angle that's occurring out on the bottom, but it's non-circular. So this one we would call a non-circular. Right cylinder. Of course, if I made it lean, it would be a non-circular oblique cylinder. Okay? So there's just various things. We talk about the shape of the bases. We talk about if it's straight up and down or if it's leaning, but they're all cylinders. Whoops, sorry about that. We also have cones. Cones are determined by a simple closed surface, which creates a base, but is not a polygon. In the plane, the base is in the plane. A point is not in the plane. The point is called the vertex of the cone. Now, you've got a picture next to yours. I've got a picture over here on my next page right here. Where do you see cones in real life?
Ice cream
cones.
around those
Sugar cones are the best example, actually. Waffle cones have funny, like, oddness to them, but sugar cones do have a really nice cone shape. Probably your best picture of a real cone in real life. You do see cones in one other place. In what? A tree? A little bit of a tree. I mean, sometimes. A Christmas tree. Yeah, I would agree with that. Overall shape. Traffic cones is the other one that you see. Again, they're not true cones because they kind of got flat tops on them, but they have that same basic overall shape to them. Sugar cone is your best example. A cone has one smooth lateral surface with no edges. It's generated by connecting all the points along the curve to the vertex. A line segment from the vertex perpendicular to the plane of the base is called the altitude. Altitude means height. It's a three-dimensional height word, okay? Altitude of the cone. You can see that the first picture here, your top picture on your page, would be a right cone. The second picture would be an oblique cone. These are both circular because why? The base is a circle. Could you make something that's not circular? Sure. Use any other shape you want. It could look very much like this picture over here on the top, where it's got that funny, shape, and then you just make it a cone instead of making it a cylinder, right? So if you had this shape turned into a cone, it would be non-circular right cone or non-circular oblique cone. Any questions on that? All right.